Our next speaker is Penelope Azuelos from the University of Bristol, and she'll be talking about a geometric criterion for detecting virtual fiber subgroups. Over to you.
Thank you very much, and thanks to all the organizers for the opportunity to speak today. So I'll speak about virtual fiber subgroups and a more or less geometric way of detecting them. There's a bit of a lie, but we'll get to that. So I'll start with a bit of background on this problem, starting with what is a virtual fiber subgroup. So this is just a finitely generated subgroup H of a finitely generated group G, such that you have these finite index subgroups H prime and G prime, which fit into this short exact sequence. So H prime is normal in G prime, and the quotient is infinite cyclic. And I guess the reason that they're called this at all is that a really important example of these is if you have a three manifold, which is which happens to be a surface bundle over the circle, then the projection will induce this short exact sequence for the fundamental groups. And this is sort of, I think, where a lot of the interest in these subgroups come from, but even just algebraically, there's a lot of information in this. So, even just about G prime, this tells you that it's virtually a reasonable semi-direct product. And then if you're interested in properties of H, this tells you a lot about the way that it's embedded in the subgroup G. So it tells you, for example, that it's separable. It tells you that there are only countably many subgroups in between H and G. So there's other things, but the point is this is a very, very strong property to have. And the problem of figuring out if a group verifies this geometrically is a fairly old one. So I'll go through a couple of results. So for here, G is finitely generated, S is a finite generating set, and H is a finitely generated subgroup. This will often be the case. And the first result is very classical, and you probably know it. So it's Hopf in 44, and he proved essentially, as he introduced the notion of ends for finitely generated groups, that two-ended groups are virtually cyclic. And you can rephrase this if you want to be a theorem about virtual fiber subgroups by phrasing it like this. So if H is not only finitely generated, but normal, and the quotient is a two-ended group, then H is a virtual fiber subgroup. Now there's a more general version that was proved by Houghton when he defined the notion of relative ends. So the notion of relative ends for a group pair, if you're not familiar with it, you like, and you quotient by the action of H on the left. This will give you a graph, and the number of relative ends of this pair is the number of ends of this graph. And what Houghton proved is that if that number is 2 and your group has infinite index in its normalizer, then it's a virtual fiber subgroup. So this is a little bit more general, particularly the assumption that on the normalizer is really much, much weaker. But there's yet another version due to Kropholler-Roller. This time, this is a paper where they introduce yet another notion of ends for a pair of groups, which is filtered ends. And I won't go into the definition because it won't come up again, but they prove that if your group pair has 2 filtered ends, whatever that is, and the subgroup has infinite index in its commensurator this time, then H is a virtual fiber subgroup. And yeah, without going into the details, this assumption on the ends is a little bit stronger than the assumption that the pair has 2 relative ends, but the algebraic assumption is a fair bit weaker. So there's something to be gained by strengthening the geometric condition. And I guess the other pattern that should have emerged from this is that each time there's some kind of geometric assumption that's being made on the subgroup or on the quotient of the Katie graph by the subgroup, and each time this is not enough to actually conclude anything, you need to assume something algebraic. And this extra thing it's a real thing, like it needs to be there. And the example I like to think about to see that is the following one. So this will be an example to show that the infinite index in the normalizer is necessary. It also shows that this assumption is necessary, but I've not given you definitions, so we'll ignore it. So this is the example. My group is going to be the fundamental group of this genus 2 surface. And I'm looking at the subgroup generated by this curve gamma. And in order to, so I mean, clearly everything is finitely generated. And then in order to figure out what this graph here is, the quotient of the Cayley graph by H, I'm just going to observe that any Cayley graph of this surface group is quasi-isometric to the hyperbolic plane. And so the quotient of the Cayley graph by H is quasi-isometric to the cover of the surface corresponding to this subgroup. So what this graph is, if I choose a correct generating set, it's a skeleton living in here, and otherwise it's quasi-isometric to it. And all that is just to say that it's two-ended. So it satisfies the geometric condition, but this subgroup fails to be a virtual fiber. It's malnormal, so there's really, it's like about as far away from being a virtual fiber subgroup as you can be. And so this trend of having to assume some kind of hopefully quite weak normality is going to persist. So I'll present a different geometric condition which can be used to spot these subgroups, and then ultimately the result will have to involve something algebraic, but this something algebraic will be a fair bit weaker than any of these assumptions. So the geometric condition in question is narrowness. I'll go through the definition, and then I'll do an example so you can see what behavior this is trying to capture. So for a graph X with vertex set V and edge set E, D is going to be the path metric. I'm really only interested in the vertices, or any subspace that I consider will be a vertex, a set of vertices. And we have this notion of coarse connectedness, which is if I give you a constant mu, some positive number, and a set of vertices, then it's mu coarsely connected if for any 2 points in the set Y, there is a finite sequence inside of Y, which goes from X to Y, and then to get from one vertex to the next, the distance is at most mu. So if mu is equal to 1, then this is just connectedness in the traditional sense, and this sequence gives you a path. And then we're just weakening that a little bit, so you're allowed to jump a bounded amount to get from one vertex to the next. And then what being narrow is so the graph is narrow if it's first of all unbounded, and secondly, for any mu in the natural numbers, there is some other constant L depending only on mu, so that if I have L plus 1 unbounded and mu coarsely connected subsets of vertices, then 2 of them have to intersect. So this is really giving you a bound scale on the number of mu coarsely connected subspaces you can find. And okay, this might seem a little bit random, but where it comes from is, so what I was interested in finding out when I started this was just, if you tell me that the Schreier graph, that the quotient of the Cayley graph by H is a quasi-line, then like when does that mean that it should be a virtual fiber? And it turns out that this is the relevant property of quasi-lines to look at. So let's see that it actually holds for those. And hopefully this should seem quite reasonable. If I'm looking for a geometric condition that is going to imply virtual fibering somehow, then if I have a quasi-line, it should definitely verify the condition. So let's do that. X is still a graph, vertices V, edges E. It's uniformly locally finite, which in our context, all the graphs I care about are quotients of Cayley graphs, so this is true. And it's quasi-isometric to the reals. So first of all, notice that you can just prove this like from the definition of a quasi-isometry. It won't take you that long. You're always going to be able to find a constant d, which only depends on the quasi-isometry constants, so that every single ball of radius d in your quasi-line separates the space into two unbounded components. This is always true, and this is what d is doing. And then I'm just going to fix mu to be something arbitrary. And now the L, the constant L corresponding to mu, is twice the maximum number of vertices in a ball of radius d plus mu, which is well defined because x is locally finite uniformly. And now I just have some arbitrary subsets of V that are unbounded and mu coarsely connected, and I'm going to get a picture. So here's X looking vaguely like a line. Here's the subspaces yi, which I've drawn to be connected, but it's fine. And the thing you want to notice is that because all of the yi's are unbounded, and because X has only two ends, this means that every yi has to have a sequence which converges towards one end or the other. But then because of how I've chosen D, so that every single ball of radius D separates, and because the yi's are mu coarsely connected, what this means is that if I take balls of radius d plus mu that are sort of sufficiently far down the ends, and because there's only finitely many of the yi's, eventually I can find two balls of radius d plus mu that intersect all of the yi's. So here are some of them. But now, okay, I've chosen L so that the number of vertices in the union of these two balls is at most L, and I have L plus 1 yi's, so two of them have to intersect. Right, so that's why quasi-lines are narrow, and hopefully this gives you some idea of what narrowness is supposed to be doing. And then why bother defining it? Well, there are some other things that are satisfied. There are some other things that satisfy narrowness, and these are so graphs with linear growth. The proof is different, and then uniformly locally finite quasi-trees with finitely many ends. And this time the proof is very similar to what we just did. You just have to deal with a slightly more complicated tree, but the idea is very similar. Any questions so far? Okay, so I'll just move on to the results then. So G is still finitely generated, H is still finitely generated, and now the geometric condition we're putting on this is that the quotient is narrow. I'm abusing notation a bit. I mean a Cayley graph of G with respect to S, but it turns out that this doesn't depend on the choice of finite generating set. So I've written it like this, and we're also assuming that this quotient has at least two ends. This is the only condition where I don't really know if it's necessary. All of the others, I have examples that tell you if you get rid of them, then it doesn't work. The two-endedness, or at least two ends, I'm not sure. So if you have ideas, let me know. But I will say a bit more about why it's required, at least for the proof that I have in a second. Okay, so then we have some equivalent statements. So first of all, H is a virtual fiber subgroup, and only if it's separable. This means that it is the intersection of some finite index subgroups of G. It has bounded packing. If you don't know what this means, you can ignore it, but the definition is there. And lastly, there are infinitely many double cosets of H. Right, so a few remarks. First of all, these conditions are all stated in order of decreasing strength. So if you don't assume anything about the about this quotient, about whether or not it's narrow or how many ends it has, then you get just from the definition that virtual fiber subgroups are separable. It's fairly standard. And then 2 also implies 3. This is a result of Yang. And then as long as you assume that H has infinite index in G, then 3 also implies 4. And again, this just follows from the definition. So what this theorem is doing is going the other way. And to go the other way, you really do need some extra assumptions, and this breaks down in general. So being a virtual fiber is significantly stronger than being separable, and so on. Right, and so the way, I won't say too much about the proof, but I do want to say a few words. So the way the proof goes is you show that 4 implies 3 and then 3 implies 1, and the 4 implies 3 is fairly short. You use narrowness to show that the commensurator of H has finite index in G, and then some results of Connor and Mahalik. And then where most of the work is getting from 3 to 1. And this is where it's necessary to assume, for the proof at least, that the quotient has at least 2 ends. Because what this tells you is there's a construction of Segiv, which will, given a subgroup so that the quotient has at least 2 ends, will give you an action of G on something called a cat-zero cube complex, which is just a very nice, very combinatorial, non-positively curved space, which is nice in and of itself. But if you add this assumption that H has bounded packing, then it turns out that this construction gives you a finite dimensional cat-zero cube complex, which is much better. And this was, as far as I can understand, so this property of bounded packing was introduced by Herska and Wise, and it sort of looks like this is the point, this is exactly the property that will give you a finite dimensional cat-zero cube complex when you feed the group to Segiv's construction. Yeah, so that's why these things are there. And then like the rest of the work is actually studying the action on a cat-zero cube complex and finding an appropriate map to the integers so that the kernel is what you need it to be. But I don't think I have time to talk about that. So the last thing I wanted to mention is why in this case we still need something algebraic. So why is it that it's not enough to assume that G over H is narrow and has at least 2 ends? Can you not just get virtual fiber subgroup from that? And maybe that seems like an unreasonable question, but a more reasonable question is, what if you strengthen this geometric condition? So what if you say, okay, G over H is not just narrow, it's a quasi-line. So it looks pretty much what you would expect a virtual fiber to look like. And it's a very strong condition to ask for. Is that is that not enough to deduce that H is a virtual fiber subgroup? And the answer is still no. But I thought the example was kind of nice. So the example in question is part of a family of groups that was introduced by Houghton. The definition is a little different, but that's where it comes from. And to define it, so we start with translations at infinity of Z. So these are bijections of the integers, so that if you just ignore a finite subset, then it's a translation. And the group is the group of all translations at infinity of the integers. So firstly, why should this be finitely generated? Well, if you think about it, a translation at infinity, this is going to be just a translation of some length composed with some finitely supported permutation. And you can generate that with 2 generators. So you can take the first one, alpha, to be just a translation of length 1, and then beta is a transposition. So we'll take one that swaps 0 and 1. And now you can get any translation you like with alpha. And if you sort of take conjugates of beta by alpha and multiply them together, you can make whatever finitely supported permutation that you want. So that generates G. And then the subgroup is the stabilizer of really any point will work, but we will take 0. And now, same question again, why should this be finitely generated? And here you can just observe that what the stabilizer of 0 is the translation z infinity of z where you've removed 0. But structurally, this is the same thing. This is still the translation z infinity of a different copy of z. So as abstract groups, these are isomorphic, and in particular, H is finitely generated. And then what does the quotient look like? So the KD graph of G quotiented by H, this is this graph here. And in particular, it is a quasi-line, so it's narrow, it has 2 ends, it verifies all the conditions, but it is not a virtual fiber subgroup. And the reason is that there are only 2 double cosets. And again, this is fairly easy to see, so one of them is H, obviously. And then to see that this contains all of the rest of G, you can just start at this coset H alpha, and then notice that the element alpha beta is in H, it stabilizes 0. And now if I just multiply on the right by this element, I can get all the way down the line, right? Alpha, beta, and so on. And then you can always go the other way. So yeah, H fails to be a virtual fiber subgroup because it fails the conditions of the theorem, but you can show sort of more directly that a virtual fiber subgroup has to admit infinitely many double cosets. Right, I'm a bit early, but that's all I wanted to say. So thank you for listening.
Thank you, Penelope. Let's thank our speaker. Does anyone have any questions?
Sorry, where did the two-endedness come in the proof of your theorem? I think you mentioned it and I just missed it, but I didn't.
Yeah, no, yeah, at least 2 ends is enough. It doesn't have to be like actually 2-ended. And it's really just to get, so from 3 to 1, I use the fact that this quotient has at least 2 ends implies that there is an action of G on a cat 0 cube complex by a construction of Seguiv, and this requires at least 2 ends in the quotient. But I have no
Okay,
idea
I
if
see.
it's
Thank you.
actually necessary. That's good.